online class as well, recording. And if at some point you can't hear us or anything, you just let me know. So welcome everyone. Most of you I've met here in person in the class. If you weren't here last time, I kind of want to bring you up to speed what we're doing this week and why we're doing this weird thing like being online, being in person, and all that. There's been a rising number of COVID cases in our communities. So for the first 2 weeks of the semester, CAC made a decision that we can offer classes both in person and online if someone felt uncomfortable. I do expect, I can't predict anything. No one knows at this time what will happen, but I expect that we will return fully to the classroom after that 2 weeks. So that's the plan. And that kind of threw me off the loop when the decision was made, because I've done teaching for like almost 20 years. I've taught this class a long time, but I had planned our class to be in person. I teach also online, and it's a whole different class, whether it's in person or online. So the syllabus and the schedule that I handed out during the first class when we met, and if you didn't get one, let me know once we get to the break, and I will make sure that you get one. It's also available online, but those might need to be adjusted if things change. What's important for me is that we go through the material, and what we go through, you get it, rather than rushing through material and covering everything possible, because there's always going to be something that we don't get. So for that reason, some of our students are joining us remotely. I do always, if I offer a remote class, I record those as well. So they will be, I'm just looking, I hope I'm recording it. I think I am. Yes. So if for some reason you know that you're going to miss a class, if you get sick or something else happens. First of all, if you get sick, I don't want you to come here. Not because I don't like you. I just don't want us all to get sick. I want us to look after each other. So if for some reason you're unwell, you're sick, you know you'll be out of town, let me know, preferably as much ahead of the time as possible. And I'll try to make sure that even if it's something hands-on, we try to record at least some of it, so you will be able to stay on track. I also, like I said, I teach this class online, and I teach this class in a middle ground of that too, like partially online, partially in person. So I have all the material already for you as the recordings, if it comes to that. But I think there's a reason why students enroll to face-to-face class. So we'll try to keep it as a face-to-face class. Another thing, in the class, we have a sign-in sheet going around, so I can give you attendance that you were here. And I need you to have been in attendance at least one time during this first week. And it's not really that I care, but the college cares, because it has all sorts of other implications, financial aid and so on and so on. I don't know what they are. I just do what I'm told, and I sleep well at night. But if you're attending remotely, it would help me a lot if you drop your name to the chat, because even though I try to remember everyone, I will forget it. Like, my attention span is that of a fly. I know we have few students who weren't able to make our first session, either in person or remotely. And there's a couple of important things we talked about. I guess that the most important thing that I can think of was the textbooks. And I told you that I'm really careful what I can say. So I'm asking, is there a student in this class, and you don't have to volunteer if you don't want, who would be willing to tell to the rest of the class what is the deal with the textbook? So I'm not saying it. That's the only reason why I'm asking. Does anyone want to volunteer? It's okay if you don't want. I'll just dance around with it. Okay. I don't have volunteers, so I'm gonna try my best. And so we have a textbook and textbook and a lab book that have been assigned for this class. And this is where it gets tricky. CAC has a contract with a bookstore chain, Barnes & Noble. And per that contract, I have to tell you that you have to buy those textbooks and you have to buy them from CAC. Would I ever enforce that? I probably would not be running after you where you bought it. But I'm supposed to say that. Can you survive through this course without a textbook? Even though there's small changes in anatomy and physiology, we know a lot of the stuff. Very few big things have changed. So I don't expect that there's a bunch of new bones or a bunch of new organs that would be significant that would have been added to a textbook from 3 years ago or 5 years ago. So you can use any A&P textbook, any version of it, as long as it's not from like 80s. It will have the same stuff. If you are planning a career in this field, like going to nursing, doing stuff like that, then maybe it would be a good idea to have the actual textbook, because it's a really good textbook. It covers everything you might need to know in basic enough level that you don't spend hours and upon hours just finding out about the simple thing. But at the same time, it has enough that you will find answer to everything. In terms of the lab book, again, it's good. How I teach, I don't necessarily give you a lot of homework. I assume that you'll figure out if you feel comfortable after the class that I know this. Or if you don't feel comfortable, you will probably go and ask me, or you will go and read a little bit of the textbook. And that's your homework. Before exam, I assume that you will prepare for the exam. I will help you to prepare for it. But again, I will not be like, you have to do these questions. So the lab book, again, it's good, but it's up to you if you feel that you absolutely need it. One more nuance to that story, and I'm sorry for everyone who's heard this already. Like, I'm telling the same stories again. Welcome to my life. Every day is a Groundhog Day. One thing that we're trying to do, or I'm trying to do, I don't always have success with the rest of my peers, but I force them slowly. I've learned that as long as I keep saying something, they'll eventually give up. In my mind, we spend too much money, or students spend too much money on textbooks. So we're trying to move towards textbooks that would be already available online. And there is a great textbook like that. I hope that this is a whiteboard. I was going to write on it, and then I started questioning that maybe I shouldn't. And I hope that this shows up also to the online class. And if it doesn't, you let me know. I'm just going to use one of them. If you go to Google and you Google OpenStax, it's with X because they're like trendy, and anatomy and physiology, you will land up to a website where there's a whole similar equal textbook as the textbook that we're using on this course for free. You can read the textbook online. You can download it. You can download chapters of it, all of it as a PDF or any reading device that we have. So again, I'm not allowed to tell you that you should not have the textbook, but just sharing this with you. Sorry, I'm going to have a look. There's something on the chat, but I'm really having a hard time following it. You can absolutely, you have the lab book online. There's a question, I have the lab book online. Can I pull it up on my computer in class, or should I print out the labs you need for that day? Any lab that we will do, I will give you what you need. You can always have computers. I don't mind if I present material and it's going too fast and you feel like you need to take pictures of things that I project. That's totally cool. I'd rather not be recorded because I get really weird about it. And I'd rather that you don't take pictures of your peers. So I hope that that answers to the question that was online. It is a good lab book, but if you haven't unwrapped it, it's still in the plastic. You can go to the bookstore and be like, oh, I changed my courses, and they won't ask a question. If you had unwrapped it, you haven't used it, you can sell it for like $5 less online, and someone will buy it. But again, I did not tell that to you. Okay. Anything else I haven't told that we discussed during the first session? I think we're pretty good. The only other thing is that this week is kind of just to bring you up to speed of where we're at and where we want to be, so that next week we start going through the chapter 1 of this course. And after next week, we jump to chapter 5, which is all about skin and associated structures, and go through system by system through half of the human body. On BIO202, we'll go through other half. But you'll notice that I skipped chapters 2, 3, and 4. They are basically stuff that you should know from your previous courses. Courses BIO181, BIO156, whatever course you've taken. So it's things like chemistry of life. It's things like, I'm trying to think what else. Basic genetics, things like different tissue types. So this week has two-folded purpose. First of all, you need to make an attendance so you don't get kicked out of the course just because someone somewhere has to do something about the attendance. So there is an activity, I think some sort of a discussion board that I put up, and I asked you to complete yesterday. If you didn't, please get it done. It's so that I know to call you with the name you want to be called and things like that. I think it adds up some small points towards your final grade. And other purpose of this week was to go through all that stuff just like as a crash course, so you will succeed on this course. So a lot of this stuff I assume that you've seen before that we're going to go through today. I think I even took the exact same slides that I use when I teach for BIO181. I just removed like all the fluff from there, and I was like, let's condense this. Only thing that I haven't got slides for, or I didn't get around to do slides for this particular class, is about different tissue types. How do you feel about different tissue types? Are you clear what I'm talking about, or you're like, I have no idea what he's talking about?
I know there are different types that don't remember all of them.
That's good. You're in a good place. So there was an answer in the classroom that we know there's different tissue types, don't remember all of them. If you're there, you're good. How about online? Anything? I think I don't see at least anyone shouting out that, oh, I have no idea what we're doing. If you feel that way, just unmute yourself and shout out. You can also use the chat, but like I said, I have a hard time following that and doing something else. I'm a guy, after all. I can only do one thing at a time. Yeah, like connective tissue, muscle tissue, epithelial tissue, and nervous tissue, things like that. That's what there was a question in the online class. So you've got it. You're at a good place. So perfect. So we have students who are good also online. So what I was going to do is that we'll just discuss through the key concepts. I don't expect it to be terribly exciting for you, but it is important that we have that. And next I'm really trying to count my days because my days keep changing around. Next Tuesday is when we're supposed to meet next time, right? I love that I have to ask from you. Unfortunately, next Tuesday, I have something else going on. I have a meeting with the college president and a few other people. We're trying to do certain things. So we will not have a class. But instead, I made a little quiz that's online that's about all of these topics that we talk about and a few other topics as well. It's a quiz that we used to use to assess if someone said that, hey, I know already a lot about biology. I don't want to take BIO201. I just want to jump right into this class. Because to do these courses, you have to have done the BIO201. So it is tough. I'm not going to lie. It is a really tough quiz. I do not expect you to get 100% for it. As long as you attempt it, you will get full points counting towards your final grade. But like at least attempt it. Don't just like go and send it blank and I'll be sad. Yes, do your best. It's also not only so that I can do an attendance for you for the next Tuesday, but it's also for me to have an idea. If everyone misses a certain question, then I know that, oh, maybe we should talk about that a little bit. But like I said, it's on a purpose really tough. Give it your best go and don't feel upset. Perfect. So what I'd like to do now is talk a little bit, and this is always hard for me when I do two things at the same time, like walking and chewing gum, not happening. I have to stop. No. So I'm trying to do two screens at the same time and talk a little bit about the chemistry of life. But before we jump there, do we have any questions at all about anything that we've discussed so far? Good. And in terms of, I know the question is that, are we going to be here for the entire time? I don't think we will, but I will be around. Normal days, I do try that we have a full class. It's just because there's so much only that I can tell you about things that you already know. I think we're going to navigate as it goes. My boss sits behind the wall, so we might not leave like immediately. No, he's good. So what do you remember about the chemistry and as it relates to biology? So we remember biology was science of life. Why on heck do you need to learn something about chemistry when you come to bio class?
Because there are chemical reactions that your body does.
Really good. So there was an answer in the classroom. I'm just repeating. Don't think that I'm being weird. So if the microphone doesn't pick it up, answer that was given was because there's chemical reactions that take place in living organisms. And that's absolutely true. Really, everything in this world is made of chemical stuff. So if we're studying things in this world, whether they're living or dead, we probably need to know a little bit about that chemistry. At the same time, I do realize you didn't sign up for chemistry class, so we'll keep it light. So that's the basic premise why we talk a little bit. And the other reason why we talk a little bit about that and why we will talk a little bit about cells and how cells make tissues is that once we get to specific body systems, I'll be just like, okay, we're going to talk about muscular system and skeletal muscle. I just want you to know what I'm talking about. That you're not like, I don't know why he went there. Or if we talk about cardiovascular system, we're going to talk about cardiac muscle. So we should have like a basic grasp. Where does that fall in the bigger picture? So everything in life is made of chemical stuff. And this sort of a diagram, not necessarily the exact same diagrams, but similar diagram might be something that you've seen before. We have letters that are symbols for different elements in the world. And there's 4 elements that we typically find in living organisms that make 96% of everything of you. And those include carbon, hydrogen, nitrogen, and oxygen, especially the carbon and hydrogen. So all chemistry of living things is based on carbon and hydrogen. And I think I should have disclosed this as well. Other than doing that quiz that you will get the full marks just for doing it, I will never ask you again these chapters in an exam. They're not in an exam. They're not something that I test you on. Fair? Good. So all of the organic chemistry is about living things, things that have been of a living sources, living organisms, living origin, is based on carbon and hydrogen. And carbon and hydrogen behave in a very particular manner. So that's why we're going to be paying attention to that. The other term that you probably have seen is matter. So anything that has a mass, so weighs something, and anything that takes up space in the universe is made of matter. And this is, again, I'm not going to test you on this, but just to explain, why did I use the term mass? What's the difference between mass and weight? Mass is just a property of an thing, object, and weight is dependent on the gravity. So weight will be different on Earth and Moon. So I'm always like, oh, I was just born to the wrong planet. That's why my weight is different than it should be. I'm sad. So we get to the elements. So elements are really the smallest unit of stuff around us that exists on its own. And I'm not talking about atoms. We'll look at small parts of atoms later on, but I'm talking about whole elements. So they're like the fundamental units that we will be focusing on when we study stuff. So really, typically, and this statement is not totally correct, but typically you cannot break down elements into smaller components in a lab, at least without great effort, and so that they would not be returning back to some other form. So we can actually break some elements apart, but they're not stable. They will then become something else very, very soon. And what you probably remember is the periodic table of elements, which lists all the elements that we know of at the moment. There are constantly stuff being added to it. So it's something that's been a document that's been around for a while, but we keep adding stuff. And you might be wondering, why is it that shape? That makes no sense that we've got number 1, and then it jumps to the other end for number 2. Number 3, 4 at other end, and then jumps to 5 to 10 on the other end. And I'm just trying to figure out how to show it on an online class so you don't feel. So number 1, number 2, then it jumps 3, 4, and then from 5 to 10. Well, actually, the layout of the periodic table of elements is super important because it tells us, if you do chemistry enough, how that element is going to behave. Like, it's really, you can read that and you can tell exactly what's going to happen. And if at any point I'm going too fast, too slow, you know already and you're bored, or I skip something and you're confused, or you just want to tell something to me, please jump in. I get really tired speaking alone. So periodic table of elements really shows you all the atoms that there are. So atoms are, again, similar to the elements, the smallest ordinary unit of matter. Atoms are what elements are made of. And if we look at this diagram, you've probably seen that when you've been told about atom, that there are 3 kind of stuff at large, if we speak in kind of very general level, that you will find in an atom. You will find some stuff at the very center of it, and again, I'm running around, at the very center of it, and that center of the atom is known as nucleus. So just like cells have a nucleus, where the stuff is, atoms as well have a nucleus. And then around that nucleus, we have stuff going around, which are known as electrons. So electrons don't actually have a circle that they're on. They're constantly rotating around the nucleus, and just to show you the plane where they would be rotating, I've drawn that circle. But really, they're just floating like planets around the sun. What's important about the atom is that these 3 different particles. So nucleus is made of protons and neutrons, and the electrons were circulating around. And they circulate in all sorts of planes. So this is just like a snapshot at one time in one plane. These three different things that atoms are made of all behave very differently. Electrons have a negative charge, protons have a positive charge, and neutrons are neutral, like the name proposes. And that will have a huge effect on the behavior of atoms. Well, first thing that you see in the periodic table of elements is that we list there the letter that symbolizes that particular element. So it's the atomic symbol. Here, helium. Here. I was going to reach, but I'm too short. Well, you also see a number on top of it, which is the atomic number. That's the order number that we've given for that. And we'll talk about that in just a second. But third thing that you'll see for each element in the periodic table of elements is the atomic mass. It's underneath that letter symbol. And the atomic mass is sometimes also called the mass number, and it tells the mass of the proton and neutron added together. Electrons have very small mass, so we don't bother. I just am all about making life easy. Oh, I had made a nice little animation. I don't even remember what happens on these slides always. We talked about the atomic number. That's how they are organized in that periodic table of elements. And one thing that we notice, that sometimes a particular element might have a different number of neutrons in it. So the number of the different number of neutrons there. So that will have a significant effect on the behavior of that element. It's still a helium, but it will behave differently. And you probably heard that those are called isotopes. You probably heard about radioisotopes before. Radioactivity, yeah. And radioactivity is directly dependent on this. So they're different isotopes of an element. So they have different number now of that stuff. They're the same thing, but if you have certain combination that's considered as an unstable combination of neutrons and protons, then it will end up behaving in a weird way, this element. And we can use it for good stuff. We can, for example, use it to age the age of an object. So I used to work in conservation restoration, like findings that they found from excavation sites, archaeological sites. And we were like, how old is this? You can actually use the radioisotopes to determine age of an object. You can also use radioisotopes in medical imaging, which is the second job that I've had. They travel with the blood. When you inject them into the blood, they travel with the blood to the areas of body where there's a lot of use of blood. And if a lot of blood is being used in a particular part of the body, we know that that part of the body is active. It's doing a lot of work. So same goes for brain imaging. We can tell that, okay, this kind of a task, if I give you a math problem, certain part of your brain will be more active than other parts when you solve math problems. So by doing that, we have been able to localize certain jobs to certain parts of the brain. Same would go that we can find for other things, that is your heart running more or less while you do a certain kind of activity. So we use it in a roundabout way for medicine, but we can use it also for bad stuff. We've seen examples from Hiroshima, from elsewhere, that radioactivity and using that in warfare can leave trouble that remains for a long time. That was really depressing. So we're back to the periodic table of elements. So the layout of that was important, and let's have a look of what we can make sense of the layout. So we have groups that are run horizontally and periods that run vertically. I always have to think about that. And that's why when we talk about different groups and periods of a periodic table, you'll just know that I'm referring to that. In terms of not only we have atoms and we have elements, sometimes these atoms like to hang out with other atoms. And if we have two or more than two atoms that are hanging out together, they form a molecule. So molecule is two or more atoms hanging out together. And we're going to have a look of that. So this is what we saw earlier on. Here we have what we call a neutral atom. So there's the same number of electrons as there are protons. There's an equal number of pluses and minuses. So if you add all the pluses and minuses together, it's going to be 0. Right? We don't worry about neutrons because we just don't. So this kind of an atom would be neutral. Now we're going to move our focus and start looking at these electrons. When we look at an atom, often you don't see all of the electrons drawn out because we're just lazy. We draw the outermost shell of electrons because it's really only the outermost shell that matters on how the atom will behave. So here we have an atom. I don't remember what it is. But in this atom, we have 3 different shells. So 3 different layers where the electrons are floating around the nucleus. And you'll notice that you can only move on to the next shell, and the innermost shell is the first shell. And then if you move outwards, you get second, third, so on, so on. You can only move on from the innermost shell to the next shell once it's full of electrons. It cannot fit in more electrons. So on this atom, it can fit only 2 electrons on the innermost shell. That's the maximum number of electrons that you typically find on the innermost shell. After that, typically on the second shell, you will find maximum of 8 electrons. On the third shell, you typically will find maximum of 8 electrons again. And so on and so on. And it gets really complicated, and there's some twists to the story. The students always ask, and I'm happy to explain, but I'm trying not to muddle the waters with the third shell especially. So what atoms want to do? They want to have a full electron shell as the outermost shell. So the outermost shell is known as valence shell. That's what we're really interested in. And atom has one goal in its life, to get that full of electrons. If it has a valence shell, so outermost shell, that's full of electrons, it's happy, it's living its best life, and it's just hanging about. If it's a little short of getting a full electron shell, it's going to do its very, very best to get to that stage that it gets the full electron shell. So we find out that we call these atoms that have a full valence shell, that are not eager to do reactions, as stable elements. They're very happy with their life. They don't need to mess about things. They don't generally do a lot of reactions. If a valence shell is not full, like in this example, we see that it would fit 8, but it only has 7. That atom is desperate to get the 8th electron there. It's like doing everything in its power. So it's going to be very, very reactive because it's only one short. It's more reactive than an atom that would have 4 electrons, because the 4 is going to like, I should, but I can't be bothered. But if it's just one short, it's going to be super reactive. So just from knowing the number of electrons, you can predict that this element is going to be making a lot of reactions. The other option would be if we have only 1 electron here. Easiest way for this atom to become super happy would be to get rid of that 1 atom. There's no point of trying to get 7 more. Let's just get rid of that one. And again, this atom is going to be super reactive. It's going to make reactions like crazy. So that's why we really focus on the valence shell. And again, here, if it gave away that one, now it would have a full valence shell and it would be happy. So that brings us to talk about the periodic table of elements again. And reason why it's important is that on periodic table of elements, where the element is sitting tells us how reactive or stable it is. You'll notice that we have elements that have a full valence shell at the very far end right side of the periodic table of elements. So they're not going to do a lot of reactions. They're just living their best life. And if they have 7 electrons or 1 electron on their valence shell, they're going to be super reactive. These elements really want to make reactions because they want to get to that full valence shell stage. Does all these ring bells? Vaguely? Totally? Like you're like, I know this.
I remember things that can be stable and reactive. I remember that.
Yeah.
Yeah, but not like them being placed on a periodic table.
Okay, well, but you're doing amazing. So just to repeat, I'm being weird for repeating, but so that no one feels online. In the classroom, I was told that people do remember kind of this thing, not necessarily to the exact same way or exact same wording. But really, this is the important concept, just to have an idea of things that might come up during this course. So only goal that the atoms will have is to get to this full valence shell. And they're going to be doing all kinds of reactions, either by getting rid of one or gaining one. That's what atoms are all about. And when an atom gets rid of one or gains one electron, they start to form chemical bonds with other atoms. So now we start getting those molecules that we talked about. So really, chemical reactions are just basically us, or basically atoms, exchanging electrons. That's all chemistry is. We're exchanging electrons. And again, please don't worry. I will not test you on this to level that it would affect your grade. It's just good to know. And you will do that quiz, but as long as you attempt the quiz, you'll get the full marks. And the quiz is online. So what we end up finding is that we talk about chemical reactions. And chemical reactions, we always have reactants and we have products. Sorry, I'm going to run here as well. So reactants and products. Reactants are what goes into that reaction, and products are what comes out of that reaction. So it's just simply a way for us to show this is ingredients of the recipe, this is the final product. And I think I've illustrated with 2 examples or few examples here. So if we have 2 hydrogen atoms and 1 oxygen atom, they spontaneously try to arrange together to form a molecule. So 2 hydrogens, 1 oxygen tends to form water, H2O. It's just something that they want to do because they all want to get that full valence shell. And they do it by giving or gaining electrons. So this is a little dumb, but I felt like, oh, let's do it. So it's similar when we talk about products and reactants as telling you a story of something. You go to the school and study. That's the reactants. Products are going to be that you're going to get an A grade, you get a great degree, and you become really rich. So that would be products. So that's the idea behind these chemical reactions. I know, that was super naive. That was the best I could do today. So we can also see that moving the other way around, that things don't build up from individual elements. Individual or molecules can break apart. So if we take 2 hydrogen peroxide units, they can break apart into 2 water molecules and 1 oxygen. So sometimes these reactions go one way and one way only. If you take hydrogen peroxide, you would see it being used, for example, for bleaching your hair. And you mix that thing. I don't have hair, so I can't speak about this. I'm trying my best. If you had hydrogen peroxide to bleach your hair, and you mix that chemical, they tell you not to leave it on a table. Or if you buy hydrogen peroxide to clean cuts and wounds, it comes in a bottle and they tell you, you should close that bottle when you're finished. That's because if you leave the hydrogen peroxide to room environment, over time, it will turn into water and oxygen. So it's like expensive oxygen that you produce by buying a bottle of hydrogen peroxide and leaving it. And then there's going to be little water at the bottom. So some reactions go only one way, that will always happen to hydrogen peroxide over time. It's hard to take water and oxygen and make it to become hydrogen peroxide. We cannot do it in our setting here now. That would require something. So these are reactions that go only one way. Some reactions can go both ways. You can take bicarbonate and hydrogen and make carbonic acid. Or you can take carbonic acid and make it into bicarbonate and hydrogen. So these are reversible reactions. They go both ways. See, I changed it around. From production reactants. I had so much energy to do this. So there's going to be, actually, you can go from carbonic acid to carbon dioxide and water. So you could basically go from one end to another either way. These are reversible reactions. Sometimes reactions can take steps in the middle, like we see here. Everyone good so far? Yes. So now the reason why I've tortured you by telling all this is what we're going to be talking next. There's three kinds of bonds that these molecules can form. So how elements can join together. First one of them is known as covalent bonds. Covalent bonds are all about sharing some of those electrons. So you see, I found a cute picture of two bunnies. They're sharing a piece of grass. I know. That's the best I could do. It was tough. So let's kind of illustrate it to make a little bit more sense. Covalent bonds are all about sharing electrons between atoms. And once these atoms share electrons, now these atoms start to hang out together. They form a bond. They're going to make a molecule. So what I have here, hydrogen, two hydrogens, one oxygen. But we'll notice that oxygen is going to have 6 electrons on its valence shell. 6 electrons on its valence shell. What does it need to become happy? It needs 2 more. Well, it just happens that we've got 2 hydrogen atoms here. And what do they need to become happy? They need to have 2 electrons on their innermost shell. So both hydrogens and this oxygen want more electrons. How can we give everyone more of something without anyone being unhappy? Well, we can do that by sharing. So now these hydrogen atoms and oxygen are going to go next to each other, and they're going to start sharing some of their electrons. It doesn't mean that all of the time this oxygen will have 8 electrons, or all of the time these hydrogens will have 2 electrons. But most of the time in their life, they're happy. They have what they need. So they take turns with handling those electrons. And whenever you're sharing 2 electrons between 2 elements, you draw a line between them in chemical diagram. So that's why it's a single line. What would happen? There's different ways how we can share these, but really the single line symbolizes a pair of shared electrons. What would happen if we have 2 sets of 2 electrons? So in total, 4 electrons are being shared. So here, again, I have an example where I have these oxygens. So they have now 6 electrons on their valence shell. They need 8 to be happy. If you take 2 oxygens, each one of them has 6, the best thing they could do is that they share 2 pairs of 2 electrons. So now, if you look at this side, everyone has an access to 8 electrons. Not all of the time, but most of the time they're happy. So now that we're sharing 2 pairs, we're going to draw 2 lines there on a chemical equation. So just an explanation where those lines come from. That's what it is. So it's 2 pairs of shared electrons. What normally happens a lot of the time is that we share those electrons equally. that both of these atoms get to hold it equal amount of time. No atom is happier than another. Sometimes it happens, though, that we share them unequally, that one atom gets to hold the electrons longer than the other atom. And this is a good example of what we have here with the water, and we'll talk about the consequences of that in a little bit. How does that make water such a weird thing? So that's the covalent bond. Does that ring bells? Yes, awesome. And again, this is just to bring you up to speed. I will not test you in an exam about this. It's just that quiz that you take. The next type of bonds that we find are ionic bonds. Ionic bonds are not sharing electrons. In ionic bonds, you completely get rid of an electron or multiple electrons, or you completely gain an electron or multiple electrons. So it's complete moving of an electron from one atom to another. So what we see in ionic bonds is that we do that giving away or gaining. And I think I have an example here of sodium and chloride. So we have 11 electrons and 17 electrons, which if you do the math, that innermost layer could, or innermost shell could include 2 at the maximum, second 8, third can 8. We end up noticing that here for sodium we have 1 on the outermost valence shell, 1 electron, and here we have then 7. So what they want to do, one wants to get rid of that 1 electron and one wants to gain 1 extra electron. Well, you put them next to each other and they will do just that. And if I remember correctly, I have a nice diagram. Now they are still the same elements, but they will have either 1 extra negative charge or 1 less negative charge. So it's not going to be neutral anymore. Like we saw at the very beginning, that's what we were trying to do, to be neutral. So now there's a slight charge in that element. And that's going to be important, this slight charge, because if you learn nothing else about life is that the opposites attract each other. And I have all sorts of fun pictures because I had a lot of time on my hands. Opposites attract each other. I know, that was slightly dumb. So now this atom that has gotten rid of 1 electron, it will now have 1 proton more than it has electrons. Remember, in the center at the nucleus. So it will have overall 1 plus more than it has minuses. And the opposite happens here, that we will now have 1 extra electron compared to the number of protons that we have at the nucleus. So the overall charge of that element or that atom is slightly positive or slightly negative. So if it's slightly positive, we call it cation. If it's slightly negative, we call it anion. And I think that just explains the very same concept. So whether you lose electrons or gain will affect the overall charge. So what happens is that, remember, opposites attract each other. So anything that has a positive charge looks for another atom that has a negative charge, and they come and hang out next to each other. This is how most salts are formed. So they're like kind of a mix of atoms being bound to each other, but they're bound because they have done some sort of an exchange of materials. Still make sense? Yeah. You've covered BIO 181. Half of it in half an hour. You should have just came to my class. I would have passed you in a week. No. You already know. That's why it's easy. The last type of a bond that we can have between atoms is hydrogen bond. And remember, hydrogen now refers to our water. And water is so special that we're going to dedicate a whole different kind of a bond for it. And we remember that most living things were made of water. Most of our Earth is water. somewhere between 65 and 75% of you is water. So if you like water, that's like when I go to a date. I'm like, if you like water, you already like me. No, I'm sad. So what you end up seeing is that these water molecules have this bond that we saw before, covalent bond. They're sharing electrons. We talked about that. So water molecules are made by being covalent bonds. They're sharing electrons. But what's funky here is that now they're not shared equally. Where the electron spends time is uneven between these parts of this molecule. So the electron spends more time at this oxygen end of this molecule. So since it's more time, the electron at the oxygen end will have most of the time 1 extra or 2 extra electrons there. So it's going to be most of the time slightly negatively charged. And then opposite happens for our hydrogen. The electron spends less time at the hydrogen end. So the hydrogen end is slightly positively charged. I'm like trying to do it all. So because the charge is uneven, we now talk about these water molecules being polar. And it simply means that they're not equally sharing the electrons that they're sharing. And this has an important consequence. So like I said, because the electron spends more time at the oxygen end, the oxygen end is going to become slightly negative. Because it spends less time at the other end is going to become slightly positively charged. And now you take a bunch of water molecules and put them next to each other. They will always arrange themselves so that the minuses and pluses are close to each other. Remember, opposites attract each other. I know, so dumb. But I try. So these are bonds. That's why water molecules stick together. Have you seen videos from space? When they drink water, it just kind of floats as a bubble. It doesn't disperse into million little molecules. It's because there's an attraction between molecules. But this attraction is not super strong. It's possible to break it. And this is why water is the key to all life. Because water allows us to do amazing things because of its chemical properties. It is a weak bond, but it's a bond nonetheless. So now we've covered all of the different kinds of bonds. And I'll just share with you real fast why water is so important. So water is described as being a universal solvent. That means that because it has these polar molecules, most things will dissolve in water. There's very few things that will not dissolve in water. In addition, this attraction of these molecules causes that you can do something like fill a glass above its rim, because remember, now those water molecules are wanting to stick together. So they're not wanting to separate. We see evidence of cohesion. Cohesion means that water molecules stick together. Evidence of adhesion is seen that water molecules tend to stick to surfaces, other surfaces. So they tend to stay on surfaces of plants, leaves, petals, so on, in the mud. Another example of adhesion, how water tends to stick to other surfaces, is if you take a jar of water and you put a really, really, really thin straw in there. Usually this is made of glass. The water will actually climb higher than the surface level of that water in the jar. It will climb up higher, up here. That's because this adhesion pulls it up. It's attached to the sides of something else. You can also see it in a glass. It kind of tends to go on the sides up. I love that some are at least nodding. Some are like, I've never seen that. I used to take my students to a lab and we were studying what happens to the leaves. No. Other thing that water has, it forms a strong surface tension. Because of this cohesion and adhesion, bugs that are light enough can walk, insects that are light enough can walk on the surface of water. So again, there's a surface tension. I have so many stories. I'm not going to go into them, but I used to train, and I did obtain my license to be a pilot. And if you have a plane and you have to crash somewhere, you just don't want to go nose down to the water. It's going to be hard as a rock because there's great surface tension. Anyone who's done swim jumping or whatever you call it in English, that you jump from high up and land to the water, you don't want to go belly first. It will hurt because of the surface tension of water. If you had only known that, someone in the class said that I've done it. If you had only taken my class, you would have known not to do that. Because what you want to do, you want to break the surface tension. So you want to go with something sharp first, like a needle edge. So preferably your toes facing first. That way you can break the surface tension and not hurt. All right. So you never crash a plane nose first to water. Water can be hard as rock. Water also is excellent in storing heat. So you can store a lot of heat in water, and then that water will slowly release that heat. And this is the reason why most people on this planet want to live at the coastal areas. If you live somewhere where there's a lot of water next to you, during the day, that big body of water, let's say we're on the coast of Atlantic or Pacific Ocean or wherever, that big body of water will during the day grab some of that heat. It's not going to get that hot as it would get otherwise. And during the night when it gets cold, it will slowly release that heat. So temperature fluctuations are not as drastic as they are here in Arizona because we just don't have water. So it gets really hot during the day, really cold during the night, as I learned when I moved here. Water can take different forms: solid, liquid, and gaseous. And water is great at transporting stuff. And this is the point that's going to be important for your A&P studies. We will see that most of the stuff is transported in things that are made of water. For example, your blood is largely made of water. So we can transport a lot of things in blood. Similarly, plants, they don't just need water. You don't water plants just so that they get water. That water will transport nutrients from the soil to those plants. That's why you water them. And those nutrients are what the plants need to stay alive. So that's why water is important. Yay! And that brings us to notice that certain things are known as hydrophilic and other things as hydrophobic. And this is dependent on the polar nature of the water. Does anyone know what a phobia means? Fear of something. I'm like, I've got only very few phobias, but like heights and spiders, snakes. Like I moved here and I was like, everything tries to kill me. What do you do if you have a phobia of something? Get the hell out of there. Absolutely. Sorry. They answered much more elegantly in the classroom than what I used. So you want to get away. So if we have a molecule or a part of a cell organelle, that's hydrophobic, it tries its best to avoid water. It doesn't want to be in contact with the water. If we have a molecule or part of a cell that's hydrophilic, it loves water. It wants to be where water is all the time. And this is going to be important because you remember you talked about cells on your BIO201 and how cells have cell membrane, the outermost layer of the cell. Yeah? I'm like looking desperately. I see some nodding here in the class. So cell membranes are made of phospholipids, which have both hydrophilic and hydrophobic part. So a single phospholipid is this kind of a ball with two legs coming out of it that you can see here. And the head part of a phospholipid is hydrophilic, so it wants to be close to water. The tail part of the phospholipid wants to stay away from water. Well, when we have a bunch of these phospholipids, they spontaneously arrange in this way that you have two layers of them, heads facing out and in, and tails facing to the middle. Now, tails can stay away from water, and out and inside of the cell membrane is in contact with the water. That's how we make cell membranes. And that's why it's going to be important. I normally talk to my class about why ice floats, why water expands when it freezes, and all that good stuff. I'm just going to jump through it because I don't want to go crazy today with the revision. And I'm just going to remind you about the pH scale as well. You remember pH told us how much hydrogen we have in a solution. So again, we're going to be talking on this course about pH of things. Just remember that we can talk about pH because we know a little bit of the basic chemistry of life. So how much hydrogen we have is told us by the pH scale. If you have very little hydrogen, you have something that's known as being basic. So you have a high pH number. If you have a lot of hydrogen, you have something that's known as being acidic. So you have a low number for the pH. And pH 7 is neutral. So pH scale runs from 0 to 14. 7 is in the bang on in the middle. Human body is just slightly off from pH 7. Human body pH is somewhere around 7.35 to 7.45. And we are able to keep it in that narrow range because we use something known as buffers. And you should have heard about buffers on your BIO201, so I will not go there. And if you have individual that has too acidic or too basic body, then you will have problems. You will get sick and it won't be fun. So now that we have talked all this stuff, there's one more thing to add to the chemistry part of the story. Remember that most of the things, living things, are made of largely of carbon and hydrogen. So carbon and hydrogen are going to be really important elements for us in anything that involves studying living things or things that were alive. So organic chemistry refers to anything that has been alive or is alive currently. So we're really all about organic chemistry, and organic chemistry is all built around with carbon and hydrogen atoms. There's always something else, but there's always carbon and hydrogen. And what's cool is that you can have same number of carbon atoms, but they can take many different shapes. And these are known as isomers. Isomers would have a same number of elements in them, same number of carbons and hydrogens, but how they are arranged is different. So the chemical formula, the shorthand when you write it out, would be same, but how you draw it out would look different. And this difference in the shape of a molecule, they're all chemically the same components, but their shape is different. This difference will have a huge effect on how these molecules behave. They will all behave very differently from each other. And what we have often, in addition to carbon and hydrogen, we have some other stuff. And these other stuff that we add to molecules are known as functional groups. And I'll leave it to that. Sorry, I didn't mean to hide it. So, do you want me to go backwards? No, this is good. So, the is what causes these otherwise same stuff to behave so differently chemically. And this is all that I was going to tell you about chemistry of life. Is anyone overwhelmed? Anyone underwhelmed? No, don't answer to that. I'm just going to live in my bubble. I'm just going to stop sharing the screen for a second for our online class so I can see if anyone typed something. I didn't mean to be rude. Absolutely. Someone had to leave for a moment, but they joined back. That's absolutely fine. I record these sessions, so if you missed anything, you can just check it out later. So what I'd like to do now is for us to take a little break, and then we'll talk about two more things that are essential, like two little mini review sessions. And then you know everything you need to be able to succeed on this class. Any questions before we take a break about anything other than chemistry as well? Does anyone feel intimidated at this point? Please do not. Like I said, I will not test you on this content, but I want to know that we're all on the same level, because it would be weird if someone has no clue about this and everyone else knows, and they spent their semester just figuring out what is a polar molecule, because then they will miss everything that I'm trying to teach. That's why we're spending that time here. Let's 5-minute break. First of all, so I can kind of like figure out what to do next, or I know what to do next, but set it all up. And also, so you can use bathroom, you can have a breather. I don't encourage you to smoke, but if you were to smoker, you can have your cigarette. Okay, we're continuing in 5 minutes. So I received a question, and don't worry, like I will tell this when you come back, but just because I don't want to be rude to the people online, I received a question that, will this be in a test? No, this will not be in a test. This is just review. I will tell you when the material that's in a test starts. Only time that you will see this material that I'm just reviewing with you is when you take that quiz online instead of our class next Tuesday. But remember, all you have to do is try that quiz. You don't have to get 100 points. You will still get full marks as long as you try. And don't panic if it looks immediately that you didn't get full marks. I will have to go and do some typing there. You will get full marks just for trying. This is just so I can have an idea that did you learn from our BIO201 class or not. The other question that I received is that, will these slides be available? This recording will be made available, and you will see the slides there on Blackboard. I think I promised to you that I will make the slides available for everything that I teach, everything except this, because I haven't prepared slides for this. But every other chapter other than this revision section, I will post the textbook slides to Blackboard. So again, if I was a student and I wanted to save my buck, I probably wouldn't buy the textbook. I would just take those slides and read them. But if I was planning to go to nursing or medicine or something else, I would be like, this is a really good textbook. I want to have it because I can refer to it when I go to the nursing school. Perfect. So we'll take that break. Sorry. Well, we're taking just a little break so anyone who's online and so on can catch up with us. Do we have any questions about anything? I know that it's a lot when it all comes at once, but remember, you've got this. Oh, I pushed somewhere that I shouldn't have. This is simply review. So again, if you're online and you have not yet posted your name to the chat, please do so I can give you an attendance. Once we get through this week, all you have to do is attend once a week, and I'm good. Of course, I'd like you to be here every time, but college will do something if you don't attend once a week. I don't know what it is. And if you know that you're going to miss classes or you're sick, just let me know, because then I can give you an excused absence. And that way, college can't do anything weird about it. So I was going to talk next about macromolecules. So when we take these molecules and what we learned, like let's talk about carbs, and let's talk about proteins, and let's talk about lipids, and let's talk about nucleic acids. But I really feel that that might be going into too much of a detail. You remember those from the past. They're different kinds of molecules, and we shall leave it to that. We'll talk a lot more about those when we get to the, for example, digestive system. We'll talk about nutritional molecules and so on. I think we're going to just jump into talking about cells. Now we talked about chemistry, let's talk about cells, and let's wrap up with a little bit of tissues. I should be sharing a screen also online that says cell structure. Sometimes when I do a lot of things, I get confused. So if you're not seeing a slide that says cell structure, you can just unmute yourself and shout that no, 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 no. Otherwise, I assume that you're seeing it. So this, again, should be a revision of a lot of things. And just so that I don't end up speaking alone, what are cells? And you can also join from online. I'm going to pull up the chat. But what are cells? Do you remember? You learned about cells. What are they? Beautiful answer. Who taught you by 181? Michael Duell. Oh, he's good. He's done a good job. So we got an answer in the class that they're the smallest unit of life. Cells are the smallest thing in this entire world that can exist being alive on its own. I have to give him kudos now. I mean, next time I see him, I'm going to be like, oh, your students still remember, because mine one's done. No, they do. I know. So cells are the smallest thing that can exist and be alive without something else to support them. So we will be looking at cells, and we will be looking everything inside the cells. So remember that the stuff inside the cell cannot exist alone. It needs other stuff. And that's why we have to go to the scale of a cell before it is capable of existing on its own. So if you recall back to your Bio 181, we talked about that you can study life in many different sizes, different scales. Sorry, I'm just trying for our online class to get a pointer out, but oh, let's go back. So I can do pointing like I would do in a classroom. So we remember we had the smallest things that were our atoms. The second top, the kind of red circle there. I can't jump that high. This one here. That's our atom. And atoms were made of those subatomic particles. You remember protons, neutrons, and electrons. If you had two or more atoms that came together, that made up a molecule. And if you had a molecule that was very large, then that's going to be a macromolecule. And the smallest thing that could live and exist on itself was the cell. And that's what we're interested in. Cells though have inside them cell organelles. I've drawn a mitochondria here. That's the reason why I don't post the exact slides, because I draw everything that I show you. And they get copyright stolen all the time. I don't doubt you, but I doubt everyone else in the world. Being suspicious. So anyways, we're going to look at the cell and what cell is made of. And then as the very last piece of today's chat that we will have, we'll see that once you take a bunch of cells and put them together, they end up making tissues. And tissues is probably as small of the scale as we will go for the most of your A and P classes. So I'm just going to jump on and talk about, oh, we're talking about this tissue. And now you remember all this chemistry story and all that, why we're talking about tissues. Of course, once you have tissues, bunch of tissues that work in a same area for a same purpose, make up an organ. If you have multiple organs that work for the same overall cause, that makes up an organ system. And if you have multiple organ systems that all work together, you have an organism such as a human. Makes sense. So we're going to focus on the cell level, the basic unit of life, smallest individual thing that can stay alive. Cell size can vary a lot, from 1 micrometer to 1 millimeter. There are cells that can be in a length of about 1 meter. Can anyone think of a cell that would be a length of about 1 meter? About this long. So I come from metric system, so I always use meters. That's what science does. So I lucked out when I was born that I was taught with the system that science uses. So if you speak to me anything else, I won't have a clue. I go shopping for stuff and they're like, how much would you like to have it? I'm like, I don't know. Just keep adding the meat to the tray and I'll tell you when I'm happy. I just don't have that concept. I struggle with conversions. The cell that's about a meter in length that I can think of would be a nerve cell that runs in your spinal cord from your brain to the end of the spinal cord. So cells can be really long, but they're tiny. It's hard to see a cell. Certain cells we can see with naked eye, but most of the time, if we want to see cells, we will need to use a microscope. And there's many different kinds of microscopes that there are, but at large they can be grouped into 2 categories. And it is the light microscopes that we use in these classes. They're relatively inexpensive. You take something and you shine light through it, or you shine light onto it, and you see a bunch of stuff because you have glass lenses that bend that light so we can see it in a very big scale. There is a way to see even smaller stuff than what you can see with light microscope, because light microscope has a limit. You would think that light travels in a straight line. If you go to the small enough scale, light starts to bend. And you cannot see when it starts bending stuff in a very, very small scale. So what you do instead then, you replace the light that you use to look at objects with electrons. You get an apparatus that shoots electrons. And you catch those electrons and you have electron microscope. Those are super expensive. Most universities where I work, we have those available, but we don't let anyone just randomly walk in there. You need to kind of know what you're doing. So we won't be talking about electron microscopy, but if you are going to take microbiome classes, you will end up seeing stuff that a lot of electron microscope pictures, because we need to go to that scale to be able to see smaller stuff such as viruses, DNA, and so on. I think if you have really good eyes, you could see with a naked eye the nucleus of the cell, but that's about it. You probably couldn't see much more. So all of this stuff, like replaying it, all of this stuff that we're going to talk about, it took quite a long time before we were able to see it. We didn't have the technology to see it. One of the questions that I always ask from my students when we talk about cells is that we concluded that cells are rather small. Even though you have some cells that are really long, they're still small. like that cell of the nervous system that connects in your spinal cord, your brain, to the end of the spinal cord. But on average, cells are tiny. And then my students are always like, why are they so tiny? It's because there's a mathematical formula. Once cell grows too big, the ratio of its surface area versus the area inside the cell, so the volume of the cell, is no longer sustainable for life to exist. So cells need to stay small enough. One way how I explain it to my students is that you can think of a gas truck that travels from one place to another. If it is too big of a truck, it will use so much gas that it will not be useful to load it with gas. It will use more gas than it can transport. So you want to keep the distances manageable so that when you're transporting something, it still makes sense to transport it. Same is with the cell. We're constantly transporting material from the outside of the cell, so from the cell membrane to the center of the cell, and away from the cell center to the cell membrane, and then it gets blocked out of the cell. If those distances are too long, it's like you are going to burn off anything that you would be carrying. It's not going to be worthwhile. Sounds familiar? Yeah. And then I have a beautiful diagram here to explain how can we overcome this. So some cells are a little bit bigger, but when they are a little bit bigger, their cell membrane, this line, that's the red line here, needs to have adaptations. And these adaptations are called either microvilli or membrane folds. I'm trying to get a pointer up for an online class. So this outer red line, and the purpose of that is to give us more surface area. So again, we have enough surface area for that volume inside the cell. So that's why you'll notice a lot of the stuff, when we look at, for example, brain, if we took the brain and smeared it out flat, the surface of the brain, it would cover a large area. If you took lungs and flattened out lungs, it would take up a large area. But we don't have human body that would be big enough to fit all that. So what we end up doing, we end up crumbling it to pack a lot of surface area in a small place. So we do the same on a cellular level as well. Awesome. Just a couple of words in case you forgot. When we study cells, we talk about cytology. When we study tissues, we talk about histology. Just terms that you might end up seeing. So here's a picture of a cell. What we're seeing is the cell membrane, so the outermost layer. And then inside the cell, there's something gooey, transparent. Then we have at the middle, roughly in the middle, this big blob. That's the nucleus. And then we've got all sorts of other things. And all of these other little things are packed inside plasma membranes. So cell structure really is that of taking a sac and putting something inside that sac. So all organelles are located inside cell membranes. And it is this compartmentalized structure of the cell that allows cell to do what it does. I think, I'm not sure what's the next slide. I think my students, I do remember now, my students often ask, how did the first cell come about? And I'm like, oh, very philosophical question. We have theories, we don't have certainty, but the best supported theories at the moment lean into that. We have this big blob that had nothing inside it. It was just this sac with a cell membrane. None of this little stuff that you see there. And then something sneaked in one day by accident. And what sneaked in had a safe and happy place to live inside that cell. And while it was safely and happily living inside there, it was also producing something that was beneficial for that cell. So it formed a symbiosis. Both of them benefited from that thing being inside the cell. And I don't remember if I did an animation or what did I do. Yeah, there's a little thing that went inside there. And now both of them benefit from living inside there. And this kept happening more and more and more. And eventually we ended up with a cell. And that is how evolution works. This took long, long, long time. But that's how things happen in biological sense in evolution. I teach in many schools, and today, this is a side tangent. Yesterday, a student was telling me that they've never seen evolution happening. Have you guys seen evolution happening? And you don't have to believe in evolution, but in science class, we assume that evolution is a fact. I used to teach evolutionary biology in a Christian university. That was a hard gig. I'm not there anymore for a reason. So evolution, I think one example that we see of evolution, and this is totally not AMP, just as a side story, is look at our COVID virus. It keeps mutating so that our vaccines are not able to catch it anymore. That shows you that evolution can happen really fast. And that's because those microscopic organelles that are our COVID virus, their lifetime is so short that they die and are born, die and get born, die and get born so many times that during all of those lifetimes, there can be significant changes. Whereas on humans, it takes us about 40 to 50 years before we get the next generation ready. Oh, I found out what that sound is in this classroom. You can sometimes hear, I think I was asking you on Tuesday that, what the heck, this is my first time in this campus teaching and I hear sounds. And then I was like, can anyone else see? And they were like, yeah, no. They were like, no. They're doing some security thing, changing the locks. That's what they're doing.
I think they were scraping chairs across the floor.
It does sound like that. Yeah, it's some sort of a changing locks project. But I was so paranoid after last time that I was like, I'm going to find out. So I'm going to tell you real short the story of two types of cells, just as a reminder. You might have heard about prokaryotes. They were the first cells that existed. This little thing that I just told you, something sneaked in inside a cell that was blank. They were first to evolve, first to come about. Very, very small cells, very simple cells. There's not a lot inside them. There's just the DNA floating around free in the cytoplasm, in the mass inside the cell. There might be some ribosomes as well. But there's not all these little structures, and there's not all these little compartments. Prokaryotes, there's a huge number of prokaryotes even today around. Even though they're simple and they were the first to evolve, they're still the most numerous types of cells we find in the world. The other types of cells that evolved much later are known as eukaryotes. They are larger in size, much more complex. There's multiple things inside them, and those things inside them are again enclosed inside these sacs of plasma membrane. And their DNA is no longer floating around free in there, it's inside the nucleus. And it is these cells, the eukaryotes, that we're interested, because eukaryotes can find other cells and start living together as groups. What happened if we had a bunch of cells together? It made a, start with T? Yes. It made a tissue. And that's how multicellular organisms come about. So these specific compartments will be an important concept when we talk about eukaryotic cells, such as cells of all animals. Animal cells are eukaryotic cells. So do you remember all parts of the cell or some parts? Just shout out what you remember. Yeah. Mitochondria. How about then starts with N? Nucleus, yeah? Perfect. This class is good. Honestly, they listed like a lot. And I'm sure online class is good. I just didn't hear you. We're going to go through them real fast. I'm going to keep it simple just because it should be a review. But really, probably the most important part that we should look at is the plasma membrane, the outermost layer of the cell. But it's also, we find plasma membranes around each of these individual organelles, cell organelles. And you remember the plasma membrane had many names: cell membrane, plasma membrane, phospholipid bilayer, all of these. And these names come for a fact or for a reason, because they tell us how it is made. And we saw earlier on when we talked about water, I mentioned that certain things are hydrophilic and certain things are hydrophobic. If we had talked about macromolecules, I would have talked about the phospholipid. So I'm going to give you a really crash course explanation of what a phospholipid is. So phospholipid has a phosphate, lipid, and fatty acid components. The fatty acids are those two legs that you can see. And then we have the phosphate group at the head part, this kind of ball-like part. And what we see is that the head part, the ball-like part, is attracted to water, and the tails were afraid of water. They were hydrophobic, and head was hydrophilic. So hydrophilic loves water, hydrophobic, the tails avoid water. So when we take these phospholipids, the chemical structure, and we put them in a liquid floating around, they will naturally organize themselves into two layers: heads facing out towards the water, tails facing inside away from the water. So spontaneously, we will have a plasma membrane appearing. And since it's made of phospholipids, and it's made of two layers of phospholipids, we call it phospholipid bilayer. So 2 for bi. And I think we already talked about this head and tail structure. Well, it's not just the cell membranes that we have that are made of, or it's not just phospholipids that make the cell membranes. We have many other things in the cell membranes. One of those things that's often embedded there is proteins. Do you remember hearing about proteins? Something? Yeah. Proteins can do many different things. Proteins are almost like the workhorses of the cell. So they can be many different kinds, but they're usually embedded either fully, true, or partially in the cell membrane. They can be channels, which would mean that they facilitate passage of material from one side of the membrane to another side of the membrane. They can actually move that material on purpose. So in that case, they would be transporter. It's like a pump. It moves material from one place to another. They can be responsible for recognizing things. For example, our immune system now to deal with the COVID is constantly looking, is there a COVID virus around me in this cell? Is this a cell or this thing that I find in my body? Is it a virus or is it part of me? So it's recognizing constantly things. They can be receptors, for example, for hormones. Not all hormones affect. I'm sorry, I don't know what to do about that. Just move around if you can't see something. Not all hormones affect all cells. For a hormone to affect a certain cell, there needs to be a receptor for it. They can work like enzymes, or they can connect cells together as junctions. Again, kind of a reminder just of what we talked. I think that we often describe cell membranes as fluid mosaic. It tells that it's constantly changing, moving. These diagrams that we see are almost like snapshots in one time. And mosaic, that it's made of many different things. We remember cell membrane is not always flat, going just around the cell. It might have these microvilli, these folds to increase the surface area, like we discussed earlier on. So everything inside the cell So we have here the cell membrane that we can see on the around the cell. Everything inside it is known as cytoplasm. So cytoplasm is this jelly-like, kind of almost transparent fluid inside the cell. It's mainly made of water, and there's a bunch of other stuff, but mainly watery. And it fills every nook and cranny of that cell. I think that's a British expression. I don't know. It fills all of the cell, the cytoplasm. But it's within the cytoplasm where we start finding these organelles that are important for us. Nucleus, one that was mentioned. What is the role of the nucleus? Well, that's where the DNA is stored. That's where the genetic material is stored. So basically instructions for doing everything that you are. DNA is this long string, and when you add some protein, it makes this kind of a ribbon-like structure that then condenses into small. And sections of the DNA that code for a specific trait or characteristic are known as genes. So every single gene that there can possibly be is inside every single cell. But not every single cell needs all of every one of those genes. So only certain genes are turned off and certain genes are turned on. So we choose what we need depending on what kind of a cell it is. What we'll notice that nucleus is surrounded by this envelope. So again, a plasma membrane layer by layer. So we call it nuclear envelope. And in there we have these little holes that allow materials to enter and leave the nucleus. DNA always stays in the nucleus, RNA might leave. Do you remember the whole story between the DNA, what DNA is, what RNA is, and what proteins are? I see nodding, and I see some that are like, oh, this sounds like fun. So again, I'm not going to test you, but you will need to know this when we get to the reproductive system. So I'm going to give a really crash course. If you know this, this is your time to meditate or do something. It's going to be like 3-minute version. So you have 3 minutes for yourself. So DNA is the genetic instructions for everything in your body, and that included the genes. DNA stays always within the nucleus of the cell. I compare, when I talk about DNA to my students, I compare it like going to a library where they have a really precious original book. And it's so precious that they let you read it only in the library at special collections, but not to check out and go home with it. That's how precious DNA is. So if we consider the DNA is instructions for everything that you are, remember that you can compare it like if DNA would be like a cookery book. You have recipes for different things. Each recipe is a gene for a certain thing. Gene for an eye color, hair color, things like that. But you never need all of the recipes from a cookery book at once. That'd be dumb to cook everything you can all at once. So cells choose which recipe do I need at this time. Similarly, cells choose which part of that DNA do I need. And the part that they need to do something that's the job of that cell is going to get copied from that textbook. And that copy is going to be called RNA. So it's like taking the special collections book, and then you can either by hand copy the recipe from there or go to a photocopier and make a copy of that. And that recipe you're allowed to take out from the library. So RNA is allowed to leave the nucleus. RNA goes to the cytoplasm, so that's jelly-like stuff that we just talked about, and hangs about there until along comes a ribosome. And ribosome is the workhorse that makes something useful about these instructions, this recipe that we wrote. What ribosome does, it collects amino acids, these little things based on the instructions written on the RNA strand and puts them one after another. So it makes this chain of amino acids. And once you have a chain of amino acids, it's called protein. So amino acids fold up and make up a protein. Now, two terms that I think you know, but just as a reminder, because we will use them on BIO202, transcribing refers to making a copy of the genetic instructions for a particular thing. So transcribing happens in the nucleus when DNA is copied, or section of DNA is copied to make an RNA. So you can think of that again like going to that library and copying that recipe. Back in the olden days, not when I was living, olden days before that, a lot of secretaries had a job of transcribing what was spoken to them. So the boss told that I want to write a letter to this, transcribe it, write it down. So you can think of it. The name of the process is to write down what you're being told. Now that we have this RNA, it has left the nucleus, it is going to be translated. Text itself, or the cookery recipe itself, does nothing good for you. It's just a recipe. It needs to be made into something useful. And translation is when we make something useful out of it. So we bake that cake based on that recipe, or we do something that makes that trait happen. So that happens in the cytoplasm of the cell with the help of the ribosomes. So we make a protein. When we take RNA and make a protein out of it, that's translating the information from the RNA into a protein. Rings bells? Yeah, awesome. Next one, mitochondria. Someone mentioned that. Often described as the powerhouse of the cell. For the longest of time, we thought that that was the only place on cell, in a cell, inside a cell, where ATP was made, where energy was made for driving the processes in the cell. Turns out there are some other things where it can happen, but still most of the energy in the cell is made by mitochondria. Mitochondria take nutrients that we consume from food and turn them into an energy. And that energy was known as ATP. So we take carbs, carbohydrates, and we convert them into ATP. Carbs come from your diet. Outside the cell, we take them in. We turn them into energy, ATP. We can use that ATP to drive other processes. It needs oxygen, and as a waste product, we get carbon dioxide, and that's why we need to breathe. On a cellular level, we need to breathe. Here's some microscopic pictures just to show that how we draw the mitochondria really is quite accurate. And I won't go into various different parts of the mitochondria. I mentioned earlier on that I spent a lot of my years doing forensic work. Mitochondria is weird. It has its own DNA. And that DNA is inherited only from your mother. And unlike the DNA that we see, normally that's just like wiggly thing, mitochondrial DNA is actually circular. If you take ever a strand, or you have a strand on your clothing, and you put it to the washer and you keep wearing it, put it to the washer, you'll notice that strand starts to unravel slowly. That happens to DNA over time. So when we have crime scenes, or I worked a lot with mummies, mummified bodies, the DNA has deteriorated so far that we cannot get a good sample of it. But we can then go for mitochondrial DNA because it's a circular, it doesn't start to unravel anywhere. It survives better. However, you can only learn about the mother of the individual from mitochondrial DNA. But I'm not going to test that in an exam. I just think it's interesting. Chloroplast, we only find them in the plants. Their job is to convert sunlight and water and carbon dioxide into sugars and oxygen. So they may store energy, solar energy, into chemical format as sugars. Only plants can do that. That's why all other organisms that plants rely on plants. We either eat plants directly or we eat someone else who has eaten plants. We rely on plants. And I just balanced off the equation that I had there. So I'll leave the chloroplast and the whole process of cellular respiration and photosynthesis, just assuming that you remember it. If you don't, you can refer back to your old notes. It's not going to be hugely important for us on this course. Different parts of the chloroplast, and that's all I was going to say about them. Endoplasmic reticulum, ER, because no one has time to say every single time endoplasmic reticulum, we just abbreviate it as ER. ER refers to this network of tubes and membranes in the cytoplasm of the cell. And there's actually two different kinds of ER. There's ER where we have no ribosomes attached on its surface, so it's smooth on its surface. And then there's ER that has ribosomes attached on its surface, and that's known as rough ER. Remember, ribosomes were the business end where we converted RNA into protein. So those are two structures that we want to know about the ER. Another cell membrane structure inside the cell. Another compartment inside the cell. Make sense? Yes? Another kind of sac-like combination of structures inside the cell known as Golgi apparatus. It's just a bunch of folded sacs and membranes inside the cell. Its function, I often describe it as a distribution center of the cell. Like if you're a trucking company, they receive goods, they transport them to the warehouse where these goods that were inside the truck get offloaded, repackaged, and sent to somewhere else. That's exactly what Golgi apparatus does. It receives stuff from other parts of the cell, repackages, organizes it, and sends it somewhere else. So that's the job of Golgi apparatus. The vesicles, lysosomes, vacuoles, so there's all kinds of other types of sacs inside the cell as well. And they serve many different purposes. They can contain chemicals, they can be storage places, or waste products, and so on, so on, so on. There are purposes for them. So again, we see this membrane sac-like structure inside the cell. So these specified compartments, we're seeing the same concept time and time again. That's why the membranes were so important for us. And centrioles are going to be important. I think you remember when you talked about mitosis and meiosis, the division of the cell. Centrioles are going to be important when we talk about reproductive system again. So they are these pair of cylindrical tubes that play a role when the DNA, the chromosomes, are being pulled to the two different poles of the cell when cell is dividing. But they are hanging about there. So I'm just going to leave it to that. You just know that there's such a structure. And that's it. That's what we need to know about it. And the final structure that I can think of is cytoskeleton. It's all of these different filaments and tubules and all other kind of strand-like stuff within the cytoplasm of the cell. It forms this kind of a two-folded function. It forms like a scaffolding that keeps the cell in its shape. If you think of building sites, they have scaffolding around the building. It makes sure that everything's where it should be so we can access things. And it also provides almost like transportation highways from one part of the cell to another. So a lot of material travels along the cytoskeleton from one part of the cell to another. So that's what I can think of to say about cytoskeleton. And finally, to conclude our journey of looking at the cell, we remember that animal cells and plant cells are very different. Animal cells, which is what our class, BIO201 and BIO202, will be looking at, are going to have soft outer layer. The plasma membrane of animal cells is kind of a more of a, it can bend, it can take shape as needed. Plant cells are very rigid because there's a cellulose wall, because plants need to grow up. They need to be able to support themselves. So their walls are thicker and more rigid. Animal cells can be connected to other animal cells, or they can be just floating around free in what we call extracellular matrix. So in this fluid between the cells. And I think that that's the level of detail that I want us to know about cells. Any questions about anything that we have covered so far? We're good. I'm looking at time as well. That's why I'm looking like everywhere. Plus, I'm half blind and the reflection is right on that. So what I'd like to do, just to wrap up our thing, we're going to talk just a tiny, tiny bit, and I don't have slides for that. So we're going to be winging it about the tissues. But in order to talk about them, let's take a quick break. And during that break, I'll have time to clear up the space. I want everyone online to be able to see what we're talking about and so on. So let's take another 5-minute break. Remember, this is revision, so do not panic too much. I really appreciate that you're so engaged, and this will set you for success for the rest of the semester. So only one more thing to go through. Let's take a 5-minute break. Thanks. I'm just going to try to see how much they can see of our board. I have no idea about time. Did you have enough time to do what you needed to do? Yeah. Let's just make a start so we get through everything. I think you should be able to see me also online and see the board behind me. So the very last thing that we need to talk about today, and then we're done with all of the revision, because I didn't prepare this. I was like, I need to make some notes for myself on the screen so I don't make a fool out of myself. And that happens a lot. We need to talk about different tissue types. So let's make notes a little bit together. And I don't have a lecture video that I have like prepared online, but I think I can load there some from my previous classes. So it won't be for this class, it will be from an earlier class, and you'll be able to see it if there's anything that I explained today that you're kind of confused. What is he on about? So we're going to talk a little bit about different tissues. Who remembers what a tissue was?
Combination of cells.
Perfect. So when we have a bunch of cells, I don't know if you can see it. I hope you can online. If you cannot, shout out or write to the chat. When we have a bunch of cells that come together, they're in the same area and they work towards a same goal, they make up a tissue. And there's going to be 4 types of tissue that we're going to be looking at today. And I think earlier on you did a great job of listing them. So I know that you know this stuff. So this should be largely a reminder. And what I think we should start with is going to be our epithelial tissues. And I'm going to change that how I divide it into 4, not the division, but just to make myself a little bit more space here at the bottom, or more space at the top so that the bottom can go a little further down. Epithelial tissues formed surfaces of different parts. I think the skin is a really good example of epithelial tissue. So they form surfaces that keep inside in, outside out, but also allow stuff to go in and out through those layers. So they protect the layers underneath, but they also allow materials to pass through them. And there's many different types of epithelial tissues, and we can classify them based on the number of layers that we have and what shape the cells are. So let's do a little graph. We have simple epithelial tissues where there's only one layer. And then we have stratified epithelial tissues where we have many layers. Everyone's still good with that. Do we remember any of the shapes that the cells could take in epithelial tissues? You're like, oh, it's there, it's there. Yeah, absolutely, you're right. So we're going to have 3 main ones. You're so close. So I'm a guy, so I get confused when I try to do two things at the same time. So please, if I misspelled something, look past it or let me know. So the first shape that we could have was squamous. So we're going to look at a cell from its side, almost like the profile, cross-section of the cell. It's this flattened disc-like cell, known as squamous cells. So if we have a simple squamous epithelium, it's one layer of these flattened disc-shaped cells. I mentioned that it's not always just one layer. Sometimes we might have multiple layers. And in that case, we talk about stratified squamous epithelium. So it's now multiple layers of flattened discs. And how many layers? That can vary. And skin would be a good example of this stratified squamous epithelium. Outermost layer of the skin is actually dead cells. And we kind of shed them. And there's underneath new layers that are then growing and eventually get pushed outside. So simple squamous and stratified squamous epithelium. Ideal for protecting structures underneath, and especially the simple squamous, which is just one layer, for materials to pass in and out through that layer. Cuboidal, what does cuboidal make you think? Cubes. So cube-shaped cells. If it's a simple cuboidal epithelium, it's just one layer of cells that look like cubes. If it's stratified cuboidal epithelium, it's going to be multiple layers of these cube-shaped cells. And my cubes are getting wonky as I draw more, so just forgive my artistic limitations. I hope you can see it online. If you can't, just let me know. The final shape that we had was the columnar that you referred to. And columnar cells look like these pillars like you described them. Again, we can have simple columnar epithelium, or we can have multiple layers of these columnar cells. There is a funky group that doesn't fall into really either one. They're called pseudostratified. Pseudostratified columnar epithelium would look like it's multiple layers in an initial look, but really it's just one layer. Because if you look, all of those cells reach the bottom, but they're kind of like looking funky. So it might trick you into thinking that there's multiple layers, but there's not really. So really the epithelial tissues, their main function to form layers, protect structures, separate inside and outside, allow passage through the materials. That sort of good stuff. Everyone good with those? Perfect. I'm thinking, can I squeeze everything on this diagram? It might be a tough call, but we'll do our best. Next one that I wanted to talk a little bit is going to be super quick. Connective tissues. What would connective tissues do? Exactly what the name proposes. It connects different body parts. So these can be, for example, bones, ligaments, tendons, all these kind of things. Even adipose tissue would fall under connective. There's one type of connective tissue that no one really thinks that it's a connective tissue, but it really is, and that's my favorite one because I love to make life difficult. Blood. Blood is a connective tissue. If you think about it, it connects one part to another. It carries. It's a special type of connective tissue. So that's all I can think of to say about connective tissues. Any questions? Let's move on to my next favorite one. I hope I can still fit it there so you can see it online. If you can't, just shout out. I'm not trying to make your life miserable, I promise. We're going to talk about muscle tissues. What do muscles do? Movement, yeah, it's all about movement. Any guesses how many different types of muscle tissues we have? 3. Let's go through those together. So the one that you probably think when you think of muscles is going to be skeletal muscle tissues. Those are the muscles that make these big muscles that we think that generate movement in the body. If we try to describe what a skeletal muscle cell looks like, it's kind of this cylindrical, like you mentioned, cylinder-shaped muscle cell. It will have multiple nuclei. So multiple nucleuses. How can a single cell have many nuclei? It's a single cell and it has many nucleus. Doesn't that contradict what we just learned?
Because of its size.
Sorry?
Because of its size.
I like where you're going. Because it used to was multiple different cells that fused together. So evolutionarily it was, or early in terms of development, it was multiple cells. Now it's one cell. Normally these nuclei are located on the edges of the cell. They're not in the center. They're kind of on the periphery of that cell. Another thing that we see in the skeletal muscle is that it has these striations, these stripes like zebra stripes that run through it. And we're going to talk about what causes those stripes and all of that once we get to the muscular system. So all that good stuff coming, but now you're kind of up to speed when we get to the muscle system. The skeletal muscles are what we're going to go to and talk about. So I think I shared with you at the beginning of the last class that what I did for a living for many years was looking at cardiac muscle. What does a cardiac muscle cell look like? So that's why it's like super near and dear for me. Yeah, it's only found in the heart, nowhere else. But it's a special type of it. We look at it as a cell level because it has certain important jobs. Did someone say something? No. I'm hearing voices again. Perfect. You got it. Sorry, I just can't tell who speaks, and I honestly am deaf in one ear, so that helps as well. You can always tell if I like someone or not when I sit in the dinner table, on which side I sit. I'm sneaky like that. So cardiac muscle cells, you're right. They have multiple branches. They're very branched. Let's think about that for a second. Why would a cardiac muscle cell have many branches? What's the job of the heart muscle? To contract, and contract in unison at the one time all of that muscle of that area. So by having these branches, the cardiac muscle cell is connected to many other cardiac muscle cells, so they can all work together and be like, hey, let's do this thing together now. The other thing that we find in cardiac muscle cells is at the end of these branches, we have adaptation called intercalated discs. And they serve the same purpose. Rather than being a cell wall, which blocks one cell from another, these intercalated discs allow messages and materials and stuff to pass from one cell to another really easily. So they make it really easy for, again, this mass of muscle, cardiac muscle, to contract in unison. Cardiac muscle cells have one nucleus, and that nucleus is typically located in the center of the cell. Final thing that we have in cardiac muscle cell is, again, these striations, these stripes. And I promised you that we'll discuss about these stripes in greater detail once we get to the muscular system. But that's why it's so important that we have this kind of shared place where we start this course from. Makes sense. Only one type of muscle left that we haven't discussed. Smooth muscle. Does anyone remember smooth muscle? Yeah.
Your stomach?
Yep, in your intestines, around stomach, in other places, around your blood vessels as well. Smooth muscle, whereas all of these other muscles, or I'm going to take that back. Whereas skeletal muscle is under voluntary control. You can choose what moves and how. Cardiac muscle, involuntary, it contracts as it wishes. But smooth muscle, you have no control again whatsoever. It does what it wants. You don't have conscious control over that. So smooth muscle cells are kind of these just blobs with a central nucleus that surround intestines. I got it from inside from the chat. Correct. Intestines, digestive system around blood vessels, and their role is in intestines, in digestive system, to form sphincters and stuff, control what moves, what doesn't move through the tube. In blood vessels, they control the blood vessel diameter. Do we want a lot of blood to go through that blood vessel or little? So they are involuntary. We cannot control them. So those are our muscle cells. We have only one group that we haven't talked about. I just don't know which colors I dare to use, that which pens come off. So we hope for the best. Like, I don't want to write something and my boss comes after me. One type of tissue that we haven't discussed. Do you remember what it was? Nervous tissue. What does nervous tissue do?
Transmit electrical signals.
It transmits messages from one part to another. So messages travel in nervous system both as electrical signals, like you said, and then between two nerve cells, also in a chemical format, in a synapses. So we're just gonna like quickly remind ourselves of the structure of the nerve cell. We will go through all this in a great detail. Like almost half of our semester this year, or this semester, is dedicated for nervous system. That tells you how important it is. We will get to dissect some brains. We will get to look at various things. You'll get to build up a whole nervous system. You'll get to see what different parts of the brain do, like I talked about that using the radioisotopes, all that good stuff. There's so much with nervous system, and it's so important no matter to what field you go, that we spend almost half of the semester on it when you come back from spring break. So let's have a look of a nerve cell. Typical nerve cell is a neuron. So typical nerve cell has two characteristics. It has a cell body, and in there you have a nucleus. So cell body and nucleus. I'm sorry, this is like probably really awkward. If you can see, just jump around or something. I would draw it twice, but I'm just afraid that if I start doing that, I'll get so confused. I'm not very smart. So just, I'll do it here. Cell body and a nucleus. So again, the nucleus serves an important role in this nerve cell. That's where the DNA is stored, but also that's where a lot of decision making happens for the nerve cell. It's almost like the brains of the cell. So nerve cells receive all kinds of signals, then they compute, what should I do with that? And then if they choose, they will pass an action potential forward. And we will get to details of all of those later on this course. So to receive those signals, the nerve cell has these little, you can think of them like little antennas coming out from there. So they are our dendrites. And the number of them, shape of them, length of them, all that might vary. So dendrites are collecting information from outside world to that cell. So the messages travel into the cell and cell body, where we process that information, and if processing of that information triggers the cell to act, what it does, it will pass a message. And the message will pass along this long string-like structure, which is known as our axon. Axon is kind of like, if you think of the telephone lines or electric lines, that carries the message from one part to another. Interestingly, electrical currents that pass through axon only can go one way. They cannot come backwards. So that's why nerve cell always passes messages a certain way. And we will talk about great detail why that happens and what it does, so you'll get like a really simplified version now. Axon might have around it fatty blobs that are known as myelin. And that I'll save to talk about that to our chapter on nervous system. But at this point, you just know that axon might be surrounded by these blobs. And actually, the purpose of these blobs is twofold. It protects the axon inside, but it also helps the message to pass quicker from one part to another. So when action potential passes through the axon, it can kind of skip the part where there's myelin around it. So it kind of is a shortcut from one spot to another. And finally, at the end of the axon, it divides into multiple branches. And there will be another axon, another nerve cell there with its dendrites collecting information from there, going to its cell body, and then it will have an axon coming out of that. So the message is electrical all the way from nerve cells dendrites to the axon terminals, and then this little gap that we see here, the message passes in a chemical format, and then it triggers a new action potential to a new cell. But that went already into more detail than I expected you to know. So if you felt like, oh, we have like a couple of months to go through all that after you come back from spring break. Now we have covered chemistry of life, cells, and tissues. These are the most important parts that I hope that you would know as we start this semester and as you move on to AMP201. I probably should give a little bit of heads up. No, not heads up, but I'll just share with you just quickly and then we'll wrap up. Most of my students say that 201 was harder than 202. And it's not that I want to scare you. I just want to explain why it might be the case. In 201, we go into quite a bit of detail about certain systems, like nervous system. So it might feel like a lot to take in. But remember, if you ace it in 201, you're going to have a blast in 202. In 202, we cover more systems, but we kind of keep it more general. So a lot of students find it fairly manageable. Next week, like I said, I won't be here on Tuesday, but on Thursday, we will start by talking about body and body cavities, body axes, different names for different body parts, all that good stuff that gives you the language that you need to then succeed in remaining of this course. And when you come back, we will study that. And the week after that, we will study about skin, all of the associated structures like nails, hair, all that good stuff. And that will be, those two chapters will be our first exam. And before you take the exam, we will all sit down, whether it's in person or remotely or a mixture of both, and we will go through the exam together. So by the time you take the exam, you've seen everything. I'm never here to catch you out or surprise you with a surprise question. You will also be doing something known as a spot test. Spot tests are very common in anatomy and physiology. Normally, in many places, it would be that there's models that we've taken out after we've studied them in a class. So once we get there, I'm just giving you heads up. And I ask you to identify the parts of the model that we've looked at together. Normally, it would be like you do it on a little piece of paper. There's A marked somewhere, B marked in another place, and so on. If we get a chance to use the clay, like I hope that we will get to use, I might actually ask you to put pins to the structures that you build. So, okay, show me where the head is. Show me where thoracic cavity is. Show me where abdominal cavity is. And we will go through all of those body parts together. But there's nothing to worry. It's not going to be tough. It's not going to be scary. And I'm okay with the first time that we do spot test together. We might even do it together. Those are what really carry the points towards your final grade. So that's why I want you to not worry about them and know that you will always be prepared, but that's what's on the horizon. Is there someone who's going to feel super upset that they really, really want homework? Because like I said, I think you know what you know. If you feel like this was a struggle, then you might want to watch those videos that I uploaded. If you feel that this was a breeze, you're set. Just go and take the quiz. When you are ready for it, there's no pressure. That quiz is due on next Wednesday because we don't meet on Tuesday. That's how you get the attendance for that. And then next Thursday, hopefully we actually get into the skeletal models and stuff. I will be okay if someone wants to attend still next Thursday remotely. I will still deliver this class, kind of this weird hybrid, but it might be harder for you to participate on things that students are doing with hands-on. So it's up to you. After the two first weeks, at this point, I think that we will be back in the class. Do you have any questions about anything? I feel like this has been kind of familiar stuff, right? Yeah. So that's all I have for today. I think I would like to wrap it up here. I don't want to keep you extra since I have nothing else to share. And I will see you next Thursday. Have a good weekend. Don't stress over things. If you have any questions, always reach out to me. You know about textbooks now. You can always message me on Blackboard. And make sure you do the assignments that I put there. I will make an announcement of that as well. Okay, that's it. Thank you. Thank you for everyone who joined remotely as well. I will actually post a picture of this on our Blackboard as well, in case anyone was like, oh, I didn't get everything. If you joined us online, make sure you post your name. If you were in person, make sure you signed in. Thank you again. Have a good day and good weekend. Sorry, it feels weird, like I'm waving to the computer. I appreciate you guys coming in person. I think we're on a better side now. I honestly feel that we'll get over this. Oh, thank you. I was going to come there. You're so nice. I was like, it's a long way off. No, thank you. Thank you. You're good. Everything you feel, everything makes sense? Awesome.
For next week, the only thing that's due is that test.
Yeah, that test, and I think you already did the discussion board, the introduction thing. Yeah, you did it, right?
Yes.
Yeah. I looked at them, but I didn't yet just grade them. So that's the only thing you have to do. And I normally don't have a lot of those things, but when I'm not here, I ask you to do. And you don't have to have it done until Wednesday of next week.
Okay.
So you have still time, and don't stress over it. It really is tough.
Yeah.
So just do your best.
Okay.
Okay.
Yeah, I already did it. So
Oh, okay. You're
I
like,
was just
I'm
like, I
done.
don't know if there's anything else I need to
No,
do.
you're done. That's
Okay,
I
perfect.
try to keep it really light.
Good.
Important for
Awesome.
me is that you like your classes.
Yes.
Okay.
All right. Thank you.
Thank you so much.
See you Thursday.
Thanks. See you on Thursday. You guys finding everything okay? Yes. Yeah. If there's anything I can help with, let me know.
So I'm Jessica because I wasn't here.
Yeah,
on
we were probably
Tuesday.
messaging.
Yeah, I messaged you to let you know.
Yeah, thank you.
But I also read over the syllabus and the
Perfect.
schedule, so I printed it out. Is it the same exact?
It's the exact same.
Okay,
I can
I
give you a
printed out
copy, but if you've
something.
already printed out your set, that was the only thing I had. The other thing that I handed out, which really is not very insightful, is like what you should do in a lab and what you shouldn't.
Okay.
I don't think there's anything there that doesn't make sense. Like, just use common sense. That's all I ask. But don't worry at all. Like, you really didn't miss anything drastic. The textbook thing is the one that I'm always afraid to say on recording. So now you know.
I also have the textbooks because my sister took this class.
That's awesome.
So another question I was wondering, do I bring both of them or should I just bring one of them? Or
We won't be using the lab manual a lot. If you want, I can tell that now look at this part of the lab manual, but I'm not expecting. The textbook is really good, but again, our classes will be like this. So if you enjoy having something where you can look at pictures, do that. But if you feel like I have already too much to carry, I don't need that. I also give out a lot of handouts. So it's up to you, however you feel. This was like a non-answer answer, sorry. But it makes sense what I'm saying.
Yes.
Yeah, awesome. And really, provided that we all return in person, we'll be doing a lot of hands-on stuff. So that's really the thing.
Because I brought both of my textbooks
Oh,
because I
that's a
wasn't
lot
sure.
to
Like,
carry.
I was like, which one should I?
No,
bring?
I
So
totally
brought
get
both.
you. And it's a little weird that we have to ask you to get something because one instructor uses it, but I can't backmount my bosses, so I'm just gonna be quiet about that. Who did your sister have the course with?
She did this like
Oh, a while
long
ago.
time ago.
Okay, yeah, no, I was
It
just
like
trying to
maybe
think
like
who it
3
was.
years
It.
ago she
Yeah,
did
okay,
it.
yeah, you're fine then. But honestly, this should be a course where you don't have to worry. I don't throw curveballs. I will tell ahead of the time what you need to know. Big thing for me is that you learn what you need to succeed. And you saw the discussion forum activity. I haven't yet graded it, so I don't know.
Yeah, I turned in my discussion. Like,
Okay, you've already done it. You're like, I'm saying. So as long as you tell me what you want out of this course, that helps me to kind of like how hard to push you.
Yeah.
If someone's like, I need that A, I will keep pushing them until they get that A. But if someone's like, I just want to pass, leave me alone, dude, I will also do that. Sounds good.
Yes.
Excellent. Well, I'm so glad to have you in this class. Thank you. Everything going good there?
Yeah, pretty good actually. And I did want to ask, so that was a quick review of what we will eventually get into,
Yes.
right?
Yeah.
And is that basically what we're doing? I mean, or will it be more in depth than that? Because I do remember, I mean, I don't remember.
We
it,
will
but I
be
know
going
I-
in more detail, but this is the foundation that allows you to understand. So after we talk about the terminology of the body and directions and stuff, we will start talking about skiing. And to understand skin, you need to know when I speak about stratified slopes and theater. Otherwise, you'll be like, what on earth is he? Thank you, bye. You'll be like, what on earth is he about? So that's why I wanted us to take this time, because at that point, I'm just assuming that you know what it is.
Right.
And if you're lost, you just shout out and I will explain it again. We will also on this semester spend time talking about muscular system. We will build all those muscles that are important on those skeletons out of the clay. But to do that, you kind of need to know the difference between skeletal muscle and cardiac muscle.
Right.
So that's the level of detail. And
Is
we
that
will.
about it?
Sorry?
Is that about all the detail we'll be going
No. We will go into great detail that why is skeletal muscle striated. We'll talk about actin and myosin fibers that make up the muscle, but it would be hard for me to start talking about them without knowing that you know what skeletal muscle is. So this is really today about making sure that the entire class is like on the same page.
Okay.
Because sometimes I get students who have done the prereq course for this 10 years ago. And they're like, I don't remember anything. And that's okay. I would get that. And sometimes I get students who have just finished it and they're like, I got this. And I don't want anyone to be from the get-go like I have no chance of succeeding.
Right.
Makes sense.
Right.
Yeah. But I really, if there is something, I explain things to the level that you need to know before the exam. And like I said, the third big component that we'll focus on this course is going to be largely the nervous system. The nervous system has so much more than just a neuron. You'll learn different parts of the brains, you'll learn what they do, you'll learn what happens, and all that good stuff. We'll talk about spinal cord in great detail, how messages come in, how messages leave spinal cord, how it carries messages from one part of the body to another. But to do that, you need to know that nervous tissue is one type of tissue.
Right.
So that's kind of the point of today.
Yeah,
Does that make sense?
Yeah, because on this, I forgot it,
but
I know it exactly.
Exactly.
When you asked me what the tissue types are and I didn't answer, I didn't remember.
But now that you
every
see, you're like, I know. And
Right.
that's all I wanted to do. I kind of wanted to bring it up to your front of your.
Yeah.
Now you're good. So I totally think that you're more than well equipped to succeed in this class. I just, like I said, I sometimes get students who have no recollection whatsoever. So I just wanted to make sure that everyone is roughly at the same place. But it's not this. You will learn new stuff. But it's this kind of stuff that you will learn. Sounds good?
Right. Yeah.
Excellent. Well, I'm so excited to have you in this class, and I honestly think that it will be a good one. I think you'll enjoy it. There's a lot that applies to your day-to-day life that you'll get out. That you'll be like, oh, now I understand what happens there.
It helps too because I do eventually want to become an RN too.
Yes.
So then this is one of those courses that's needed.
It's needed, and then when you go to nursing classes, so I do teach nursing somewhere else, they assume that you have all of this information that you learn from these courses. They will not go back like I went back to explain things. It's just assumed that you're ready to jump on, and when they say humerus, you know what humerus is.
Somewhere down here.
You're doing good. You're doing good. So we will also cover on this semester the skeletal system, joints, and so on. And all of that really, it just comes down to that. I just want to make sure that you know when we talk about bone, that you know that it's a connective tissue. So kind of that sort of stuff. I really don't expect there to be anything that is super surprising or super tough, but we'll add layers of knowledge on top of that.
Okay.
Excellent. Well, I do something fun for the weekend. I really appreciate you being part of this class, and I look forward to working with you.
It helps too that you seem, well, like a real great teacher, and you're not just a teacher, but you're personable. You're a person behind the teacher, if that makes sense.
Well, I appreciate that. I think teaching is a tough job, and we all have different styles of doing it. So I hope that this will work for you. If it doesn't work for you, I totally get it. If you say, no, I'm going to take 202 with someone else. Everyone has a different style. Everyone has different background. Everyone has different stories. But I'm always eager to do the best I can. So if something doesn't work for you, something doesn't make sense, or if you're like, I'd like to hear more about that, feel free to ask, and you're already doing it.
Yeah.
Like, I love that in a class, that you ask questions, because it gets really boring if I tell the same story every semester. I want to tell what's interesting to you.
Right, and then, yeah, that's one of the reasons I like it. You tell me stories that are keeping me interested. I once had a teacher, wasn't bio, but English,
Yeah.
and she just gave us science. She was just kind of there.
It's tough, and I totally get it, because I've not been that teacher, but I've been in those classes.
Right, yeah.
And sometimes it is that the topic can be just that hard, that there's nothing exciting about it, and you just have to learn. That happens sometimes. Sometimes it's just that, like, personalities, some gel well together and some don't. It's not that one would be bad, it's just not a good match.
Right.
So
yeah.
there's all sorts of things. And my goal is really, depending on what happens with the pandemic, that's my big kind of unknown on this. Normally from these classes, I try to make sure that if my students want to go to nursing classes, we'll go for a couple, so you'll see what it is. And I think that that motivates you as well, because you know what to work towards once you've been in a class. But I can't promise it just yet, because with the pandemic, we've made a deal with my contacts at the nursing that let's not take students just yet. Let's wait what happens, because they need to keep the nursing department running, and they already have COVID cases, so
Right.
we can't add more to that. But there's a couple of things coming up. I'll tell about health fair that CAC throws every year, I think. And there you get to interact with current nursing students who are showing what they do. And they will do various things, health-related things, measure your blood pressure and so on. But they will also give you a chance, you get to talk with them. How is it to study nursing? Do you want to study here? Should I have studied somewhere else? And they'll tell you the truth. Because they're students. Like, students always tell the truth to another student. So I think you'll be super fun. I honestly think you're already a couple of steps ahead of the curve. So just enjoy that and keep asking questions. And if I'm not here and you have a question, just send me the question and I'll try to answer.
Yeah. Sometimes too, I get worried too. Like, I'm sure I've asked, like, in this type of class in high school, I've asked a lot of questions. We're on the same subject for a while. Like, I can tell the teacher's patient worse than.
No, I don't mind. I honestly don't. It makes my life nicer. I'm going to be honest, I teach the same class, I think 3 or 4 times a week. So it's nice when there's something new. Otherwise, I'm like, I could have just recorded it and played it. So it keeps me on my toes as well. So I really appreciate it.
I just worry about holding up the whole class.
No, you don't. If it was the case, I would tell you, we'll do it after class.
All right.
So let's make a deal. You have a good weekend. Do something fun. You too. Thanks.